Welcome to today's webinar. The topic today is modeling and stress analysis of solid models in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the content of the website, the German and English webinars, newsletters, customer projects, and so on. I will be the moderator today, and I will answer your questions during the webinar. Yeah, and my colleague Lukas Süle will do the presentation. He's responsible for product engineering and customer support. And yeah, he's, for example, the main responsible person for the development of the interfaces between RFEM RStab and other programs such as CAD programs. Okay, then I say some words how you can ask questions. Let me switch off my camera that you can see the full screen. You can press that button with the question mark above. Then you can enter your question here, press send, and then I will receive your question and I will answer you during the webinar. Okay, that should be all from my side. I hand over to Lukas. Lukas, you can start.
All right, thank you for the introduction, Andreas. I continue with the content of today's webinar. In previous webinars, which were related to the stress strain analysis add-on, we modeled a lot of beam and surface structures. This time I wanted to mix it up and model a solid structure. That will also be the content of the first chapter, modeling and loading of a solid model. And in the second part of today's webinar, I will do a stress analysis in the basic RFEM 6, but also using the stress strain analysis add-on. Concerning this example, I have to say it's made up. It's not a real example. I just made it up for today's webinar. I would call it maybe as an Excel support or support of an Excel, with the idea to have a material saving design, let's say for the use in the aviation, for example. So that is the model for today. For such models, often you have like a step file or a DXF file as a basic, at least, where you can refer to, which you can use as an help for the modeling in RFEM. And this is also what I would like today what I would like to do today. So I have here I have here a 3D DXF file for that structure. As you can see it here, it contains the main outlines, dimensions, and yeah, it makes sense to import that information into RFEM 6. That's what I will do now. So we hop right into RFEM 6 and we can run the import without creating an RFEM project first. So we just go to File, Import DXF. Then we can select the DXF file that we want to import. And we should get an import dialog in a second. And this import dialog has a couple of functions. On the left, we have functions to place the content properly in RFEM. Maybe we have to rotate it depending on the global Z-axis or so. And on the right-hand side, we have additional options. For example, an option to generate members from lines. Usually you have only lines in a DXF file. But if the line is assigned to a specific layer that has the name, let's say IPE 300, then a vertical line, and then the material name S235, then you can use these information from the layers to generate members based on lines. Alternatively, we have additional, we have options to, let's say, import layers as visibilities, or even import information from selected layers, in case we have multiple layers in the same DXF file, we can control from which layers we want to import the information. I have just one in here, so this function is grayed out. And yeah, and the last option here is the length that we can assign to these DXF files. Basically, the default is automatic. That means we read the unit system that has been used in the DXF file. You can define the units in AutoCAD, for example, or for DXF files in AutoCAD. It should be, that is actually a good question. Let me see. I just know the German name and did not prepare the English name. I'm sorry for that. Yeah, units. Okay, makes sense. With units, we can call up this little dialog, and here we can set the unit for this drawing. Here I have millimeters, and if this unit setting is defined, we can read it automatically. So we know that the lines that we read are in millimeters, and yeah, we have them in the right length in RFEM afterwards. If you do not define the unit for a DXF file, you probably have to select the unit here manually. Okay, so far regarding that, let's run the import, and then we get the same information that we just saw in AutoCAD here in RFEM. Now, I made the experience that working with DXF files can also be tricky because of double lines, double nodes, all this stuff which I do not want to have in my RFEM model. Yeah, I want to have a clean structure, and therefore I will use the necessary information and get rid of anything else. What is important for me to know is, of course, the shape of that whole model, which I will keep, of course, but the thickness, for example, that's just an information that I need, 20 millimeters for the main part, and then we have these 10 millimeter additions for this bolt support here on the top. So what I will do now is following. I will create a view from the front and remove all the lines that I do not need. So I get rid of all those lines, and also here I will delete most of the lines, and now I can take a look from the side again, and this is what I want to keep, and everything else I will create myself in RFEM 6. There are some nodes which have no function. You can see it here, the line is going through. There's just nodes flying around. I get rid of them. Also here, this arc or the circle is not made of one line, but was divided by multiple lines, which I do not want to have. I want to have one big circle. So I will create the circle again, which is no problem. I will simply, well, before I do that, I want to make sure that I'm working in the right work plane. It's a small model, as you can see, and my work plane is quite big. So what I want to do is I want to modify the work plane according to my model. So I will change the space for my grid points to 10 millimeters, and I also want to have it dynamically according to the size of the model. So I don't want to say I want to have 30 or 100 grid points. It should be sized automatically. So now let's zoom in. What I can see now is that it's still in the wrong plane, so I will switch it to a vertical plane. And now I feel much more comfortable modeling something because I know where my elements will end up. I also place this plane on my existing structure, not that it's, I don't know, maybe 10 millimeters in minus y direction or something. Yeah, now back to my original thought. I will create a circle simply by clicking here at the center point and one of those nodes. The inner circle, actually, I want to split up. I can do that quite easily with the right mouse button on the line, say divide with one node, and now I have two arcs. That will be helpful for later on when I define my contact solid. All right, looking good. Now I want to create two surfaces, one big surface for this lower part, let's say for this beam-like part, and then one surface for this bolt support. Before I do that, I split up this outer circle on two nodes, on those two nodes one more time, like that, so I can select the boundary lines. I can create a circle by selecting the boundary lines, and the surface or the stiffness type of that surface will be without thickness. We are modeling solids, so all dimensions are existing in the model itself afterwards, so the boundary surfaces of those solids usually have a zero thickness. They have no stiffness at all. So now one more surface for that part, and now I will create the openings, also quite easy. We just select the boundary lines for those openings, and there we have it. Now the next step to create the main solid is via an extrusion, basically, and that's also how the command is called in RFEM, extrusion. Before we do that, I want to check the local coordinate systems of those surfaces. We get it as a information by hovering over the surface. You can see it here. The local z-axis shows to the right now for that surface, and for this surface to the left. That's not ideal, because when I extruded either in the minus or the negative or positive local z coordinate. If I do it at the same time for both surfaces, they will end up in different directions. So I will turn the coordinate system of one of those surfaces, reverse local axis system. Now they show both in the same direction, and now I can extrude it. I select the surfaces and hit the extrude, or use the extrude function into a solid. The solid should have the thickness of 20 millimeter. That's what we measured basically before. It's an S235, and I hit the apply button. Now I have these two solids, and as you remember, we had these reinforcements, let's say here on the top. It was a bit wider, the support for the bolt, for this axle. So I will add another solid on both sides. I can do that quickly by using the drag and drop functionality of RFEM 6. So I select the solid, that's what I want to copy. I also hit the control button and grab a specific node, and then I release this copy on that node, and I created a copy of that solid, and now I can modify it because it has a thickness of 20 millimeters, and actually it should only be 10 millimeters. So again, I use drag and drop. I use it really frequently. It's a really nice feature, and I just drag it to the center node of that new line. Now it's a 10 millimeter thick solid. Now I select the solid again and use again drag and drop to copy it to the other side. It's much quicker than using mirror functions or anything like that. Okay. So far regarding that part. Now let me define these material saving areas, if we want to call it so. I will first of all define my work plane in a plane where I want to define these surfaces. So I set it maybe to that plane, and I will also hide all the objects that I do not care about. And I don't care about anything else except of the lines, nodes, and surfaces that are lying in my current work plane. So I make this kind of selection and hide the rest. I can also hide it completely. And now I only see basically the first surface again that I modeled here today. And yes, and for creating these material saving areas, I will modify my snapping a bit. So I have these new icons on the bottom right here in RFEM6 where I can directly select or deselect certain snap functions. I can also right mouse click and go into the edit option or into the edit menu and have it here in one window. And I would like to use the feature parallel today and parts of line and set here 30. So this will create 30 snap points on each line, which I will use to freely model these areas. Okay. What I also want is I would like to have like a thick flange running around this this model. So I will basically copy that line or the outer boundary lines inside, and I can use again specific features for that. We have here also nice options on the bottom. For example, we have an option to create a center line or to create an angled or a round corner that I will use later. And here we have the one that I'm looking for, create new parallel lines. That's what I will use. I would like to create a parallel line with a distance of 7 millimeters. And now I need the direction, and the direction can be defined here. Now we only have to check the local coordinate systems of those lines. We can see them directly. Yeah, it will be shown while we are in that. Yeah, while we use that feature, then they will disappear again. And I see that I have to define them in the negative local set direction. So I select the lines, hit the enter button, and then I will change the offset direction to positive local set. Select the other lines, hit again enter, and from those lines to the inside of this plane surface I will create these material saving areas. Okay, let me start here. I actually have a little drawing here, and I will start creating new lines. Again, it will be like a free modeling. So let me just grab some of those points that I have in mind here. Yeah, these are these 30 division points on every line that I have. And then down here, snap point 12. And that is the first area where I want to reduce the thickness. Then I can continue. Yeah, this will take a few moments, but not too long. And here, point 14. And then from here. Oops, sorry, misclicked a bit. Now we can take that too, doesn't matter. All right. Just some of these snap points. Now for that line, I would like to have a line somewhere ending here, but it should be parallel to the existing line that I just draw. And therefore I activated that parallel snap, and it's working in following way. You just hover with the mouse over that line that you want to have a parallel line for until this yellow cross shows up. And if you create your line now and it is just somehow parallel to the existing one, you will snap that parallel line, as you can see here. And now I can move along that line and define my node, for example, here. And from here, I will go into the direction of this bolt support and then to the top again, like that. All right. Now, I have two more of such areas here. Again, I would like to have a parallel line to this diagonal one. I move my mouse on top of the line, and not on these grid points, but on the line itself, and grid snapping points. And then I'm catching again the parallel line, maybe from here to here, and then just a few more from here, further down, maybe here. And we close it down here. All right. So these are the lines that I wanted to create. Now I will connect them. So because currently, I'm working with this option, auto connect lines members turned off. That means whenever I model a line or a node onto an existing line, it will not divide this line. I want to have full control over this division. So I turned this option off, and now I can create division on those points where I want to have them, where this small feature here, and I just draw a window over those areas where the lines should be divided. So for example, here, and down here too. Not sure if I catch this before. Okay. So now they should be divided, as we can see here, and I can use this feature to create a round corner from the bottom icon list. Quite easy to use. You define the radius for this rounding, and then you select the two lines. And this again will take a short moment. It's just a bit of work. Those roundings are there on purpose because I would like to avoid sharp edges and so on. As you know, we are using here finite element software or analysis. So any sharp edge could cause singularities, and to avoid them, we create round corners. So, all right. Concerning that line, I want to modify it a bit. I actually would like to have like an arc here, maybe via the edge nodes and the definition of the radius. So I select the node and also that node. Oh, come on. Now I'm catching some. Sorry, I should have turned off these division points and other snap points first. Okay. So, and now I can create like the radius graphically, and I will just use something like that. Okay. I will remove the remaining nodes and lines that I have now. To be fair, they would not interfere with my results at all. As long they have no function, that means as long there is no load placed on those lines or they are not supported, they will not affect our results at all, not even the mesh. But anyway, I would like to have a clean model, so I get rid of this stuff. Okay. Goes to as well. Okay. Now, these are my surfaces. I can show the complete structure again and model actually real surfaces based on these boundary lines. Why do I want to do it? I would like to create a solid for those surfaces which is reaching into this structure, and then I will use a bool like a subtraction, of solids, like feature like that, to create these reduced areas. Before I do so, I will run some plausibility check or model checks, for example, identical nodes. Sometimes you create stuff like that, which is the case here, but you can easily handle them. You can say unite nodes and delete the unused node. All right, so that I did. Let me also intersect. Should I not? I don't think I need to do that. And yeah, now I can create these surfaces again by selecting the boundary lines. That should be quite easy. Yes. All right. And yeah, now we can create a solid. So let me quickly do it. The solid can be created via an extrusion, as I showed it before, or also via the function move copy. So that's an alternative way, which I also want to show. So I have here the manipulation move copy. I can create a copy of that surface that should be created 7 millimeters in minus y direction. Should go into that existing solid. And now we can select here so-called step links. And I would like to create a solid while copying the surface. You can imagine it as a linked extrusion to that copying. If I copy that surface to any other location, I have like a vector and I can extrude it along the vector so I get a solid. That's all. Let's press OK, and we have these additional solids. And now in a second step, I mirror those solids to the other side of my structure because I want to have these reduction areas on both sides. Right mouse button, missed, manipulation mirror. I create a copy. It's the XZ plane where I want to mirror it on, and I really should turn off my additional snap points. Anyway, I catch the center, press OK, and yeah, now I have it on both sides. All right, yeah, let me turn off the snap again for those parts. All right. So now we can do this subtraction. This is quite easy to handle. We select the solids that should work as a subtraction. I edit them and I change the solid type into whole. So by pressing OK, it will do this subtraction. It will generate a new solid with these areas as wholes, basically. And then we can change the generated type. Now it's like a generated surface. We can cancel this generated state and we get a regular solid out of it. Pressing OK. No. Okay. And after doing that, I simply remove all those additional solids that I modeled and I delete it, including the boundary surfaces. And now the big solid remains, but including the holes. And I could do this step again and again and again. I could create now an additional solid, maybe which somehow interacts with the main solid, do this subtraction again, convert it into a regular solid, do one more time. So that's much better compared to RFEM 5. All right. I'm not done yet with the modeling. What I also need is a contact solid. So what I would like to do is I would like to model the bolt or this axle, and it should, of course, transfer forces into that supporting beam here. It should, however, not be glued to the existing structure. I want to have like a more realistic force transfer. And I can do it, for example, via a contact solid. So a little solid that is going around this hole, and then I can control how should the forces in perpendicular be transferred, and but also, like in both directions, basically. So I want to model this small solid first. That's also not too difficult. I will modify my grid again. Say here 1 millimeter, 1 millimeter as distance. And I also want to show only the objects in that plane, like that. And now I can model this small inner solid. I will create 2 lines, 1 millimeter here from the top and the bottom. And then an arc by selecting the end nodes of the arc. And for the radius, I can select this center point, which I have here. That is the center point of that arc. And yeah, so I get the right radius for my new little arc. Okay, that's all for now. I can create a little surface, again by selecting the boundary lines without any thickness. Oops, I guess I modeled somewhere again. Duplicated node, yeah, there are some. So I'm using the same command again. And now let me try it without thickness. Yeah, now it can close the area. Okay, I will cancel the visibility mode, and I will extrude this surface now into a solid a couple times there for each solid that I have here. So I simply say manipulation, move copy, create a copy. The distance I can pick graphically. I know it's 10 millimeters, but yeah, you can also pick it graphically. The vector for copying, and it should also create a solid by doing so. That's the first one, and now I can continue. Just selecting the surface again. Move copy, now 20 millimeters. Okay, and one more time. Again, 10 millimeters. Okay. Now I can mirror them to the other side. Mirror in the YZ plane. And for the center, I'm using that node, for example. I press OK. All right. These are the additional solids that I need. And now I just modify them and change them from a regular solid, standard solid, into a contact solid. I can define the details of the contact solid. So the force transfer perpendicular, but also parallel to the contact surfaces. Obviously, there should be no force transmission when there is tension between these surfaces, so between the bolt and the support, yeah, so failure under tension, and parallel to my surfaces, I might have friction or whatever. I can basically get rid of it because I do not have any forces in that direction. So I just define here a small rigid friction. Now all these solids are incorrectly defined. That's because the the contact surfaces are not correctly defined, we can quickly do that. I go into this dialog and select my contact surfaces. And yeah, that's again just a little bit of work, but nothing complicated. Right, and for the other side as well. You can see that I'm turning all those red solids into black ones basically here, so everything is good, correctly defined. All right, so these are the contact solids, and now I can model the bolt or this axle. I just select my lines here again, or these two arcs. Use again the command move copy. I create one copy. It should be 60 millimeter in plus Y direction. And this time I don't want to create a solid or anything like that, but actually a surface. Yeah. Okay. So by copying the line, I extrude them into a surface, and I will close that surface or that pipe, what I have now. I think it's visible. I will close it on the end by using a rigid surface and not without thickness. I will explain it afterwards when I talk about the loading. Yeah. And now I mirror it one more time in the XZ plane. I select my node for the plane, and I have it on the other side as well. Now I can create my remaining solid for this axle. So I create manually this time. That is of course possible as well. Default solid, and I select the boundary surface. And here my recommendation is, if your structure is getting a bit more complicated, then the autocomplete function maybe should be turned off. I prefer to select the surfaces manually, then I know that I am catching the right ones. And yeah, I do this all manually. Okay, and that should be it. Let's see if no, probably I picked something incorrectly. Let me take another look. Oh yeah, I missed that one, of course. All right. Yeah, now it's correct. Yeah, again, the solid is black, or displayed here in black, so that's good. And yeah. All right, so far regarding the modeling. Now let's continue with the support and the loading of the structure. Concerning the support, I will simply create surface supports inside these holes. So therefore I use a surface support, a rigid one, and I simply select this inner surface by selecting these lines here. Okay. And the icon is a bit big, so I can easily change the size for that. Okay. So it's much more clearer how this structure is supported. And concerning the loading, I also want to do it quite simplified here. In general, regarding solid loading, we have, of course, so-called solid load, yeah, which you can assign to solids, either a force, a temperature, a strain, or additional force types, load types, and you can enter the magnitude. In my case, I simplified a bit. I just want to have two loads, two basically nodal loads, acting on the boundary surface of that axle in a, let's say, 45 degree direction. to spread the load, this nodal load, which I will apply in a second, equally over the whole bolt, I defined here this rigid surface. Of course, I could do it much more detailed, maybe by modeling here another solid or divide this surface into additional parts and place my loads also only on those parts of this bolt or axle. Again, due to time issues, I try to simplify it a bit here. So I create a node in these center points. Then I place my working plane one more time in that area. I will also change a bit the dimension or the distance for the snap points, and I create 2 more nodes, basically just one for the moment here. And now I can create a nodal load. And usually those nodal loads are acting in the global coordinate system. Either you have just one load in one direction, or you use here the components input, then you can access all 3 directions and 3 rotations at the same time. I use this type force, but with a specific direction, 10 kilonewtons, specific direction. And here I can say direct this load to a specific node, for example, this one. And then I can assign the load onto that node. And yeah, I have a nodal load acting into the direction that I want, without having to deal with rotations or anything like that. Now I select my load, one more time this point, and also this one. And I use drag and drop to put it to the other side, to copy it to the other side. And again, I already have a correct defined nodal load. Yeah, so far regarding the modeling and the loading. The next step would be checking the FE mesh. That's of course quite important for solid models. So what we do here, before I do it, just let me check one more time for identical nodes. There's nothing. Just intersect all lines again. And now let's try to generate a mesh. Therefore, I'm checking the mesh settings. And the default length that we define every time is 0.5 meter. Yeah. For that example, it doesn't make any sense. Yeah, it's way too big. So I will start maybe with a 10 millimeter mesh. And I expect an error message about the epsilon. So I already modified and assign here a smaller value. Let me generate the mesh. All right, so meshing is done. We can see here that we have only 2 elements over the width. That's not enough, I would say. Yeah, I want to have much more. So that's one reason already to increase or decrease the mesh size. And yeah, also for other areas here, I have only 1 element over the thickness. That's not enough. So I have to modify the mesh. There's also another way how you can check if the quality of the mesh is good or not. At least it could be one feature that helps you with the decision or with the checking if the mesh is okay or not, and it's called mesh quality. It's in the display navigator. We can select it and maybe show it only for solids, not for surfaces. And then we get in a little statistics on the right hand side. We can see for solids, I have 88% with an okay status, 12% with a warning. Yeah, failed is not relevant here, but it's quite a high number of, let's say, FE elements with warnings. But what does warning mean? It's basically just a geometric check. If you go into the mesh settings one more time, you have here quality criteria for these FE elements. So that is about, let's say, the ratio, of the length and the height and so on. How big are they deformed? And depending on these criteria, they output a warning or a failure, which doesn't mean that you can't calculate the model. It just helps you to understand the quality of it, the mesh. So let's optimize it a bit. I go again into the mesh settings, and instead of 10 millimeters, I use 4 millimeters here. Okay, and apply. Let's see how the mesh quality will, hopefully improve. All right. So now we have 98% with an OK status, just 2% with the warning. I accept that for now. That it is also looking much better now. I think that's clear to see. Yes, so let me turn the quality off again. In that area, let's say I would like to have an even finer mesh, so I can modify that further. What I do not want to use is, I don't want to use the global target length for finite elements, because that might create smaller elements in areas where I already have enough. So what I actually want to use is, let's say, a local finite mesh refinement. And you can assign it on many objects. You can assign a mesh refinement on nodes, on lines, on surfaces, or even on solids. So I'm selecting solids where I want to have a refinement for. So that are these 3 solids. Selected again with the navigator. I edit those solids and I create a mesh refinement here. The target length should now be 2 millimeters. That will obviously delete my current mesh. And now I will mesh it one more time. Good thing about RFEM is that you don't have to draw the mesh manually or something like that. This will all be done by the mesh generator. You just have to give him some boundary information for that job. What's the target length in that area? What's the target length for that area? And he will consider these settings. So looks quite good in my opinion. And that's now the situation where we would start with the analysis. Before we do it, maybe one more little information about load cases and combinations. I'm doing it very short here today. I'm not digging deeper into that topic. But in general, we would create load combinations for that structure, because we need it for the design in our add-ons. So let's go through that through the process quite quickly. In the first sub dialog here, we can define the code we want to have load combinations for, and in case of the Eurocode, the national annex. Then we can define our load cases. I just have the permanent dead load case here today, and I assigned my loads into that dead load case. Probably technically not correct, but okay for today. Next step is the design situations. For which design situation do we want to have load combinations for? I'm only curious about the ultimate limit state today, according to this formula from the Eurocode, and then I get my load combinations here. So this is all regarding the combinations. I think there are other webinars that explain it much further. Now, regarding the calculation, we have 2 options. We can calculate it, let's say, locally on the PC you're sitting in front of, or you can send your model into the cloud. If you do that, you can pick different PCs for that calculation with, I don't know, many cores, which could be beneficial in case of long calculations. You basically upload the file into the cloud to the PC. There it will be calculated, and then you get information when the calculation is done, and you download it again with the results. Today, I want to do neither of that because the calculation takes around 6 minutes, and yeah, I don't want you to wait for the results. Therefore, I have the file with results already opened here, and it's the exact same file, and anything from here I will show on that file. So what do we get after the calculation? We get, of course, a result navigator where we can display, for example, the deformation of the structure. Yeah, that's always good to check if it's deforming according to your expectations. And I think we can see that here. Let me turn off the mesh for a second. The bolt seems to be in contact with this support, and it will also be released from let's say the tension side of that axle, and we can also double check that, for example, by checking the stresses. So instead of the deformation, I will show now my solid stresses. For example, the equivalent stress from according to Mises criteria, and to see the stresses inside that axle support, I will simply create a small visibility by only showing these three solids. So visibility by selected and related objects. And now we can take a look inside this solid, or inside the stresses of the solid, and we can see clearly that there are stresses on the side where we pulled from, but basically no stresses on the opposite side. So that tells me that the contact solid is working correctly. All right. What else do we see if we check the stresses on this model? We see in general a lot of blue. Blue means we are here in a really low stress area. So I guess we can definitely reduce more, or get rid of more material here to save weight, or alternatively, we could optimize the areas where we have stress peaks. And we can see we have a peak here in that area where we are connecting, let's say, this main beam, to this axle support, to the circular solid. That's not ideally solved. You would probably have a much smoother transfer or material transfer here, and this would optimize the stresses in that area. So that could be modeled additionally. It's no big deal to create here additional arcs and lines, then a surface extruded into a solid, and you have this additional material on top there. So far regarding, let's say, the basic RFEM results, deformation, stresses, obviously support reactions, we can display here. And this is what we get in RFEM 6 directly. What we do not get is a design ratio. We just get the existing stresses. For a design ratio, you might want to use the stress strain analysis add-on. We can activate it in our add-ons. Here, stress strain analysis. And now we have this additional add-on here in the tables. And we can quickly check if the input data is correct. The default is always to analyze everything that we have in a structure. In my case, it doesn't make sense to analyze any surface because they have no thickness. And concerning the solids, we also see that solids 17 to 22 are invalid. These should be my contact solids. I also get no stresses for them. For the rest, I get a design ratio. We also have solid configurations similar to surface and member configurations, where we can control which stresses should be shown, or even the limit stress if it is not, let's say, a basic stress limit. So if you are looking for defining a user-defined stress limit, you just switch it here to user-defined, and then you have access to the limit stress column. Yes. So this is okay. And with that information, we can already run the analysis or the design in that add-on. Yes. And as expected, we get, first of all, an overview table. The overview table shows up if certain designs are not fulfilled, which is the case here. Yeah. The stress limit, this existing stress is higher than the limit. We can also have a look at the stresses for each solid, for example. There are different subtables this add-on gives us, similar to a design for surfaces and members. Yeah, I think this is quite clear. How could we take a look at which ways are there additionally to have a look at the stresses? Yeah. Now I only showed how you can disable or how you can hide certain solids, but what if I would like to know the stress inside a solid? There are different options. Some of them can be found here under the guide objects. And here I want to highlight the clipping plane, but also the clipping box. There are some predefined clipping planes for each, default plane, X, Y, X, Z, Y, Z. And in my case, I would like to have like vertical cut through my structure. Therefore, I'm activating here the clipping plane for X, Z. Of course, you can create your own ones too. So I turn it on, and for a better visibility, I turn off the show clipped areas. So now I have a clipping plane vertically, except in the XZ plane. I can move it manually, and by doing so, I get the chance to take a look at the stresses inside those solids. Yeah, that's one way. The other way would be a clipping box. Then it's a three-dimensional box with the same handling, or a result section. A result section won't hide the other stuff as the clipping plane does. It just creates like a vertical section in your structure, which shows those stresses in that area. So let me create that too. We can do it via this icon, set new result section, and I just have to define 2 points. Before I do so, I will put my plane into a proper position, my working plane maybe into the center. Now I can define these 2 points from here to here maybe, and it should be dragged into the global Z direction. I press OK, and it will show me the stresses in that section. As I said, we do not hide other objects like in the clipping planes. We just display these stresses in the section. And it will be much more clear if we, let's say, select here the stresses according to Mises and maybe turn it off for the solids to see only the stresses inside this section. Yeah. All right. Yeah, these are the ways how we can display stresses in solids. Concerning the peak stresses that are above our limit, as I said, we can either optimize it by adding a bit of material here on these locations where we have where we are above the limit, or alternatively, we are also able to run a plastic analysis for solids. To do so, you need the add-on for material nonlinearities, nonlinear material behavior. That's the additional add-on that would be required. If you have that, you can go into your materials and change the material model from isotropic linear elastic to isotropic plastic for surfaces and solids. And this, if you run the analysis afterwards, the stresses are, of course, limited by the yield stress, and then you can check the plastic strains and so on to see if you're still in the limit for the strain analysis. Yeah, so far maybe regarding that. And the rest for today, for my part, should be the documentation of that little example. With that, I want to close it. And the documentation usually means a printout report. And this we can, of course, also create in RFEM 6 itself. Let me quickly show it. In the data navigator here, we have the printout report on the bottom. I will create a new one. In here, you select, actually collapse all, you select which subtable do you want to display in the protocol. Yeah, do you want to have a table for the materials, for the lines, for the surface, and so on? So it's like a global selection of the content of your protocol. And if that's done, you can take a look at the protocol first, maybe. Just a second. All right, here we have it. Like an overview paper, then the contents, and then we have all these subtables that I just mentioned for materials, for lines, for surfaces, and so on. And now you could, optimize the protocol by printing graphics into it. To do so, I just minimize or put it to the other screen that I have here. And the question is, how do you print graphics into a protocol? That is actually quite easy. You basically just show the graphic that you want to have in the protocol here in the main window. So let's say we would like to have an additional graphic for this structure in our protocol. I will just hide my section. Maybe like this. This could be a nice graphic. And I would like to print it into the protocol. Then I have this little icon here with the printer icon. Say print graphics to printout report. And maybe make it window filling. And that's maybe okay for now. Let's wait for the little update. That's the graphic I want to have in the protocol. I press OK, and I can already continue. The next graphic that would be nice to have in a protocol to understand how the loads are acting is maybe that one here with the load arrows. So again, I call up my function print to protocol. This time, let's say it doesn't have to be over the full page size. Maybe 50% of the page size is enough. Let's run the update of the little preview, and then we can press OK. All right, and maybe the last picture related to the stresses. So therefore, I activate my results again. Oh, did I change something? Maybe, no, I think I just have the results for the combination, not for the load case. Let me cancel the analysis for that. Otherwise, we would have to wait a couple of minutes. Yeah. All right. Let's see. Yeah, we have results for the load combinations or for the stress strain analysis. I did not calculate the load case because, it doesn't matter in that case. For my load combinations or for the stress strain analysis, then I have the stresses, and let's say that could also be a graphic that I would like to see in my protocol. So same function, print to protocol, and this time I click save and show. So let me put it back to the main screen. And what we can see here now is that we have these 3 additional graphics. And these graphics are also placed on the proper location. Yeah, I have this overview graphic in my, let's say, model data topic. I have the load case related graphic under my load cases, under load case 1, and the stresses are in my result tables. So you don't have to move all the graphics around because they are placed at the end of the protocol. There is some kind of logic that places it already according to the chapter the graphic is dealing with. Yeah, that's the way how you can optimize your protocol. And at the end of the day, you can maybe export it into a PDF file. Then you get all these little links here as well that you have here in our navigator. You get also in the PDF file. So it's quite easy to navigate through the protocol. Yeah, and that is already all from my side. Let me say thank you for your interest. I hope I was able to show you some new features and functions. And yeah, have a nice day. Andreas, I hand it back to you.
Thank you, Lucas, for your presentation. An additional hint from my side, you can book your free online appointment, such as a product demonstration or something like that. You can click on that link at the bottom here, or you can scan the QR code on the right side. Yeah, just contact our sales team. You can get a product demonstration of our main programs, of the add-ons, etc. Okay, that should be also all from my side. Thank you for your attention. Thanks to Lucas for the presentation. I wish all a nice rest of the day. Bye bye.